In this video, we're going to think about enthalpy and calorimetry, how we can determine the enthalpy for a solution and how we can use calorimetry in order to identify the enthalpy. So we know that heat and work are exchanged in a reaction. So we already know that delta E equals Q, which is heat, plus W, which is work. And so the enthalpy for a reaction, so H is equal to E plus the pressure times the volume. So if we were to think about delta H is the change in enthalpy. So just like energy, it's really, really hard to determine the enthalpy at any given point. So delta H is going to be equal to delta E plus P delta V. We know that delta E is equal to Q plus W. And previously we learned that work is equal to negative P delta V. So work equals negative P delta V. And so if we exchange this out, we will see that it equals plus negative W. So the two W's cancel. So delta H equals QP, where this is the heat at constant pressure. So if we know that delta H is equal to Q, we have thought about how we can calculate Q previously. So we know that Q of the system is equal to mc sub s delta T. So how much heat does it take to change the temperature of a substance? So we know that delta H equals QP. Again, this P just means constant pressure. And in these videos, we are only going to consider delta H at constant pressure. There is a way that you can consider the change in enthalpy at constant or changing pressures, and that would be delta H equals QV, which means constant volume, and that's slightly different. So if we know what we already know about state functions tells us that the change in any state function is equal to the final minus initial. So in terms of a reaction, the final is the products and the initial is the reactant. So we can get this information. So in this video, we're going to think about how you can calculate delta H. But we want to think about what does it mean if delta H and therefore also delta or QP is positive. Q positive means that heat is absorbed from the surroundings. Therefore, delta T is negative, and that means that this reaction is, in fact, endothermic. So this means that the heat is going into the reaction. When delta H is negative, heat is lost to the surroundings. So the heat is leaving the system to go to the surroundings. Therefore, the change in temperature is going to be positive. So we can see that this is positive, it is lost, and last but not least, that makes this an exothermic reaction. So we can think of that as something that gets hot to the touch as the reaction occurs. So we can start to think about the charge on that. An endothermic means that the energy has to go into the solution or into the reaction in order to occur. And when it is negative, it means that the energy or the enthalpy is going to exchange. So as we continue to think about delta H of a reaction, delta H of a reaction is how much energy it takes to go from start to finish. So we've thought about this in previous videos, and we're going to think about it in the next couple of videos in this series, but we're asking how much energy does it take to go from start to finish? So in this case, the delta H of the reaction is negative 2,044 kilojoules. Now, this here is often thought of as kilojoules per mole, but it's kilojoules per mole of what? So it is negative 2,044 kilojoules per 1 mole of C3H8, or negative 2,044 kilojoules per mole per 5 moles of O2, or 3 moles of CO2, or 4 moles of H2O. So these per moles come from the balanced equation. So we can start to think about the change in enthalpy relative to the amount of product consumed, product created, or reactant consumed. So in this case, what is the change in enthalpy for the reaction if 62 grams of O2 is combusted? So we know that it is negative 2,044 kilojoules for 5 moles of oxygen. So how many moles of oxygen do we have? So we're going to take our 62.0 grams of O2. We're going to convert that to moles using the molecular weight of 32.00 grams of O2 and 1 mole of O2. Then we're going to multiply that by the negative 2,044 kilojoules for 5 moles of oxygen. So this is going to give us change in enthalpy of negative 792 kilojoules. Now this is not per mole, this is just standard. So we could do this for any reaction as long as we have a balanced chemical reaction and delta H. So we know that ammonia reacts with oxygen gas to form nitric oxide and water. So we would like to calculate delta H in kilojoules if 155 grams of ammonia is used in this reaction with excess oxygen gas. So in this case, we're going to take our 155 grams of ammonia, which is NH3. We're going to divide by the molar mass of 17.04 grams and 1 mole of NH3. And then we're going to multiply this by the delta H of reaction, which is negative 906 kilojoules divided by the 4 moles of NH3, and that gives you negative 2,060 kilojoules. So this answer only has 3 sig figs, and so this is the correct answer. So if we have delta H, we can convert that into the type of reactants or products that we have based on the balanced chemical equation. So are there ways that we can determine delta H of reaction, maybe in the laboratory or in certain experiments? So for an aqueous reaction, we can use something called a coffee cup calorimeter. Now a coffee cup calorimeter has several parts. And so I'm going to draw a schematic that looks similar to what you would see. So it turns out that there are 2 styrofoam cups. And over that, we have a lid. So we have 2 cups. We have a lid. Down here, we have a stir bar. And then we're going to have a poorly drawn thermometer, which will be submerged under some liquid. So these 2 coffee cups need to be styrofoam. And the reason they need to be styrofoam is so that the heat transfer from your hand or elsewhere is not going to be observed. So the change in temperature is going to be measured based on the reaction occurring. So we can calculate Q solution or Q reaction. We know that Q solution is the heat in the water. Q reaction is going to be the opposite of Q solution. So we can start to think about these equations. So Q solution is going to be equal to the mass of solution times the C sub S of solution times the change in temperature. This is quite similar to the other ways we could calculate Q, which would be the heat required to change the temperature of a substance without a reaction occurring. So we know that energy cannot be created nor destroyed. So the energy created in the solution, or Q of the solution, is equal to negative Q reaction. So we can actually solve for this equation, where Q reaction is equal to negative M C sub s delta T, where these two are of the water. And the M is going to be the total mass. So if we know what Q reaction is, we can convert that to delta H. So delta H is equal to Q reaction per mole. And it's typically going to be specified. So per mole of reactant, and this would just be the amount of moles that you would create in your solution. So let's look at some examples. So magnesium metal reacts with HCl to form magnesium chloride and hydrogen gas. If 0.158 grams of magnesium combines with 100.0 mils of excess HCl, where the density of that solution is going to be 1.02 grams per mil, in a coffee cup chronometer, the temperature raises from 25.6 to 32.8 degrees Celsius. What is delta H reaction per mole of magnesium if C sub s equals 4.184 joules per gram Kelvin? So it's asking us to find delta H reaction, and in order to do that, we need to find Q reaction. So Q reaction is equal to negative M C sub s delta T. So C sub s, found in the problem, 4.184 joules per gram Kelvin. Delta T is equal to 32.8 minus 25.6, and this is going to equal 7.2 degrees Celsius. It's also going to equal 7.2 Kelvin, because 1 degree Celsius is equal to 1 degree Kelvin in terms of delta T. So now we need to figure out the mass, but the total mass. So the mass of water plus the mass of magnesium. So we're going to take our 100.0 grams of water, multiply that by a density of 1.02, and that's going to give me 102.0 grams. So the total mass is going to be 102.0 plus 1.58. Whoops. Hold on. That's going to actually equal 0.158 grams. And in order to get this correct, I'm going to change this 100 mils to be 100.000 mils so that we can use the entirety of the mass. So we'll add our 0, 0 here and our 0, 0 here. So I'm going to get a mass of 102.158. So now we can just plug this into our equation, where negative 102.158 grams multiplied by 4.184 joules per gram Kelvin multiplied by 7.2 Kelvin. When you plug this into your calculator, I get negative 3,077.5 joules. Now this question asks for delta H reaction per mole of magnesium. So we need to figure out how many moles of magnesium this relates to. So to determine N of magnesium, we're going to take our 0.158 grams, divide by 24.31 in 1 mole, and this is going to give me 0.00650 moles. So delta H is equal to negative 3,077.5 joules divided by 0.00650 moles. And this is going to give us negative 473,461.5 joules. This is the number on your calculator. We can only have 2 sig figs based on delta T. And so this is going to be negative 4.7 times 10 to the 5th joules per mole. And that gives you delta H reaction. So in these calculations, if it asks for the heat exchanged, you're just solving for Q. If it's asking for delta H of reaction, you can determine that as well. So let's look at another example. So in this case, we have a 6.50 gram sample of solid sodium hydroxide, and it's going to be dissolved in 100 grams of water in a coffee cup calorimeter, the temperature rises from 21.6 to 37.8 degrees Celsius. Calculate delta H in kilojoules per mole sodium hydroxide for this process. Assume that the specific heat of the solution is the same as that of pure water. So again, we need Q reaction is equal to negative M C sub S delta T. So in this case, M is going to be 6.50 grams plus 100.0 grams. And that's going to give me 106.5 grams. C sub S is equal to 4.184 joules per gram Kelvin. And delta T is going to be 37.8 minus 21.6. And that gives you 16.2 degrees Celsius or 16.2 Kelvin. So we can now go ahead and plug that into Q reaction, which is going to equal negative 106.5 grams times 4.184 joules per gram Kelvin multiplied by 16.2 Kelvin. So that equals 7,218 or negative 7,218.7 joules. And so it asks for this in kilojoules per mole of sodium hydroxide. So we need to figure out the moles of NaOH. So we're going to take our 6.50 grams of NaOH, divide by the molar mass, which is 48 grams per mole. And that equals 0.1625 moles. So delta H is going to be equal to negative 7,218.7 joules divided by 0.1625 moles. It asks for it in kilojoules, so we'll go ahead and do that conversion of 1,000 joules in 1 kilojoule. And that equals, so that gives us 44.423 kilojoules per mole. And based on our supplied answers, we can have 3 sig figs, which gives us 44.4. We lost our negative sign. Let's bring it back. Kilojoules per mole. And that equals delta H of reaction. So we can do this for any samples. We can do this for any conditions, as long as we remember it's the total mass times the specific heat times delta T.